Good morning, dear students. A happy welcome to you all for the prestigious TSMS webinar sessions. Myself, Mrs. Sridevi Polu, Principal, TSMS Pudur, Vikarabad District, is privileged to be a part of this webinar team. And today, it's a time for the atomic structure children. And this is a session 4 by Mr. B.NAGESWAR garu, PGT Chemistry from TSMS Jakranpalli, Nijamabad. So dear children, in the previous sessions, Sir has taught you regarding the atomic number, atomic mass, then spectrum, hydrogen spectrum, and Bohr's theory, isn't it? And today is the time for quantum numbers. So what are these quantum numbers? And the address of an electron in an atom. See, where the electron is located in an atom, in which subshell, and what is the shape of that orbital, and what is its magnetic orientation, and is there any spin for the electron? Yes, of course. And what are the different types of spins it is having, whether it is rotating in the clockwise direction or in the anti-clockwise direction. And then regarding the filling of degenerate orbitals. What are degenerate orbitals? Orbitals of nearly equal energy, same energy are called as degenerate orbitals. How they will accommodate? So they will enter into the lower energy level before entering into the higher energy level. Okay, so about all these things, Sir is going to explain you with many examples, and he is going to give some numericals also. And we are going to give the important questions which you will get from this chapter, that is atomic structure. So good morning, sir.
Good morning, madam.
Good morning, Naishra, sir.
Good
Yeah,
morning, madam.
please
Good
welcome
morning.
to the webinar session. Yeah, I think
Thank you.
it's
Thank you.
the last session by you regarding
Yes.
atomic structure, isn't it, sir?
Yes, ma'am. Yes, ma'am. It is the last session.
Yeah, today you are going to discuss about what topics? Could you brief them?
Okay, ma'am. Mainly today I will discuss about quantum numbers. After that, how to filling electrons in orbitals. So for that, some basics are there: above principle, Pauli's exclusion principle, Hund's rule of magma multiplicity, and moreover n plus L rule also I will introduce. Okay, ma'am. So stability factors also, when atoms are stable. So these factors I will introduce today, ma'am.
Yeah. So dear children, sir is going to discuss about the stability factors also. Means if the orbitals are half filled, incompletely filled, then completely filled, how does the stability factor affect, sir? So I would like to hand over the session to Mr. Nageswar garu. Thank you, sir.
Thank you, ma'am. Thank you very much.
Please take over the session.
Okay, ma'am. Very good morning to all. So myself, B.NAGESWAR, PGT Chemistry, TSMS Jakranpalli, Nijamabad District. Madam already introduced me. So dear children, already we discussed 3 sessions. Okay, in first session, second session, third session. So we discussed so many concepts about atomic structure. Okay, in that already we discussed so what are the subatomic particles, what are the atomic models, okay, what is the photoelectric effect, what is Planck's quantum theory, okay, what are the Bohr's atomic model for hydrogen atom. These things already we discussed in last sessions. Okay, so till now we discussed 3 sessions, children. Okay, for better understanding, so you again see the previous sessions also. Okay, then you can gain the complete knowledge about atomic structure. Mainly in the last session, in the session 3, we discussed the Bohr's atomic model. Already I said, children, it is very, very important for 8 marks. Already we have an idea about intermediate exam pattern. In that one 8 marks question definitely come from atomic structure. In that mainly 2 topics are there. One is Bohr's atomic model, other one is a quantum numbers. Okay, so in the last session we discussed completely about Bohr's atomic model. Mainly in today's session we have to discuss about quantum numbers. Okay, what we discussed in the last session, just see children, Bohr's model for hydrogen atom, dual behavior of matter, de Broglie equation, Heisenberg's uncertainty principle, quantum mechanics, quantum mechanical model of atom. These topics we discussed in the last session. Now in today's session, what we discuss? The mainly quantum numbers. After that, shapes of atomic orbitals, energies of orbitals, filling up electrons in orbitals, above principle, Hund's rule of maximum multiplicity, Pauli's exclusion principle, stability of completely filled and half filled orbital. Children, this session is very important. Not only for IP, other competitive exams also it is very important. Generally in IP, one question we expect from quantum numbers from this session. We definitely expect one question from quantum numbers. The remaining all the topics, shapes of atomic orbitals, energies of orbitals, so whatever topics I have given in this session, all are important for competitive exams. That means MSET, IIT, NEET, okay? These type of exams cover these topics. They are very important, and moreover, these are very easy topics. Easily we can do the answers. Okay, children? Right, you go for our session. Yes, so our interesting topic is quantum numbers. Okay, quantum numbers. Already in previous session we discussed what are the orbitals. In previous session we discussed what are the orbitals according to quantum mechanical model of an atom. What is orbital, children? What is orbital? Where the probability of finding an electron is maximum, which is revolving a orbit, where the probability of an electron is the maximum, which is revolving in a orbit, that is known as a orbital. If you want to know the, electron, where the electron present, what is the energy of the electron, what is the shape of the orbital, where the electron exactly present, to find out the position of electron, so what we need, so many things we have to understand about by quantum numbers. That means atomic orbitals. What are the uses of quantum numbers? Means atomic orbitals are precisely distinguished by quantum numbers. Each orbital designated by 3 quantum numbers. Mainly 3 quantum numbers. Actually, quantum numbers are 4 types. Quantum numbers are 4 types: principal quantum number, azimuthal quantum number, magnetic quantum number, spin quantum number. By use of first 3, principal, azimuthal, magnetic quantum numbers, we can understand. Okay, we can understand completely about atomic orbital. But if you want to know the spin of the electron exactly in orbital, we have to discuss about spin quantum number. Right, children? Now we go for discuss one by one. First one, principal quantum number. Principal quantum number. Very easy concept. There is no complication in this topic. It's very easily we can understand. Simple, children. Principal. What is the meaning of principal? Principal means main. Principal means main. That is, it is the main quantum number compared to the all the quantum number. Principal quantum number was proposed by Niels Bohr. It can be represented with letter N. How we represent, children? Principal quantum number we can represent with letter small n. The values of n are 1, 2, 3 are K, L, M, N. Now we are seeing one sentence: 1, 2, 3, 4, otherwise K, L, M, N. That means these are indicates. N indicates here orbit. N indicates here orbit. That means shell. Already we know, children, one point, orbit. We can also call as a shell. Orbit or shell or energy level or stationary states. Okay, these are the same meaning words. Okay, synonyms these are. The values of n 1, 2, 3, 4 are K, L, M, N. That means it identifies the shell. It determines, that means principal quantum number determines the size and large extent the energy of the orbital. That means suppose that so many orbitals are there. Okay, 1s, 2s, 3s, 2p, 3p, 3s, 3d, 4f. So many orbitals are there. In that orbital, which have more size and more energy. That is explained by principal quantum number. Okay, children, understanding what I am telling? Very simple, children. Principal quantum number was proposed by Niels Bohr. It can be represented with the letter small n. The values of small n is equal to 1, 2, 3, 4 or KLMN. These letters or these numbers are indicates shell. Okay, next it determines, principal quantum number determines the size and the large extent the energy of the orbital. Next, children, if you want to increase, suppose that what happens, children, we are taking the numbers 1, 2, 3, 4. That means the value is increases with the increase of n value. With the increase of n value, then what happens, children? If n value is increases, then energy of the orbit also increases. That means, what do you mean by this sentence? Suppose that we are taking n is equal to 1. N is equal to 1. N is equal to 1 means what, children? It is a first orbit. Suppose we are increase the n value. N is equal to 2. N is equal to 2 means what, children? N is equal to 2 means it is a second orbit or second shell. That means if you are moving from first orbit to second orbit, then what happens, children? Then energy of the orbit is increases. That means with the increase of n value, energy of the orbit also increases. Next, children, number of orbitals present in a principal quantum number, principal quantum level, that is equal to the n square. Number of orbitals. Suppose that we are taking one particular shell. First shell we are taking. Okay. We have a doubt. How many orbitals are present in a first shell? To know that easily we can understand by using n square. N is equal to here numbers. N is equal to principal quantum number. N is equal to 1, 2, 3 and so on. What we are taking here? First orbit we are taking. Now value of n is equal to 1. Therefore 1 square is equal to 1 only. That means in the case of first orbit or in the case of first shell, what we have? We have only one orbital. That is a 1s orbital. Okay, children, understanding? Number of orbitals are present in a principal quantum level is equal to n square. Okay, suppose that we are taking a second orbit. Okay, second orbit means n square means 2 square. 2 square is equal to 4. That means in the case of second orbit or second shell, we have totally 2 square means how many? 2 square means 4. We have 4 orbitals. Maximum number of electrons that can be present in a principal quantum level is equal to n square. Why we are taking here 2n square? Because of in each orbital we can fill maximum 2 electrons only. In each orbital we can fill maximum 2 electrons only. That is why we are taking 2n square. Maximum number of electrons that can be present in a principal quantum level is equal to 2n square. Suppose that we are taking one principal quantum level 1. That means first shell we are taking. How many electrons are present in a first shell? To understand this easily, 2n square. 2 into 1 square is equal to 2. That means in the case of first shell or in the case of first orbit, we have only 2 electrons. Suppose we are taking a second orbit. Second orbit means here n is equal to 2. Substitute in 2n square. Then we will get 2 into 2 square. 2 into 2 square means 2 4 ja 8. That means in the case of second orbit, we have 8 electrons. Similarly, we can find how many electrons are there in a particular orbit by using 2n square. So now, what is the significance of principal quantum number? Simply, already we discussed. Significance. What is the significance? What is the importance of this one? Significance. The principal quantum number explains the size and energy of the orbital. Remember, children, actually, quantum numbers, based on the quantum numbers, a question will come for 8 marks. What are the quantum numbers? Write about quantum numbers. It is actually 8 marks question. For every principal quantum number, we have to write significance. For writing of significance only, we have 4 marks. Significance of principal quantum number, we have 1 mark. Significance of azimuthal quantum number, we have 1 mark. Significance of magnetic quantum number, we have 1 mark. Spin quantum number significance also have 1 mark. That is why you have to remember significance very carefully. Definitely you have to remember. If you're for writing a significance only, we have a marks in IPE. Okay, children. What are the principal quantum number significance? Very simple. It explains, principal quantum number explains size and energy of the orbital. Okay, children, right? It is simply about principal quantum number. Easily we can understand. Principal quantum number. Principal quantum number. Who discovered principal quantum number? Who proposed principal quantum number? It proposed by Niels Bohr. It represents with small n. The values of n is equal to 1, 2, 3, 4 or k, l, m, n and so on. If n value increases, then energy of the orbit also increases. Number of orbitals are present in a principal quantum number, that is equal to n square. If you want to find electrons, that is equal to 2n square in a particular orbit. Okay, it explains simply size and energy of the orbital. It is the significance of principal quantum number. Next, you go for azimuthal quantum number. Easily we can understand. Azimuthal quantum number also called as a subsidiary quantum number. It is also called as a subsidiary quantum number or orbital angular momentum quantum number. Azimuthal quantum number has 2 names. One is the subsidiary quantum number. Next one is a orbital angular momentum quantum number. It was proposed by Sommerfeld. We can represented by small l. The values of l, the values of small l depends on completely n values. The values has a range from 0 to n minus 1. Remember children, it's very important. L values, L has values from 0 to n minus 1. If we are taking n is equal to 1, just to substitute in previous one. Okay, if n is equal to 1, then n minus 1 means 1 minus 1. Then what we will get? L is equal to 0. If we are taking n is equal to 2, then L is equal to 0, 1. If n is equal to 3, then we can get L is equal to 0, 1, 2. How we are getting, children? Easily we are getting from n minus 1, because of already we know L has values range from 0 to n minus 1. It is simply about azimuthal quantum number. And some more points, children. The number of subshells in a principal shell. The number of subshells in a principal shell is equal to the values of n. What do you mean by this sentence? Simple, children. What I am explaining here, the number of subshells. You have to remember one word, children. Orbitals are subshells. Both are the same. Orbitals are subshells. Both have same meaning. Next, orbit, shell. Both have same meaning. Orbits also known as shells. Okay. Orbitals also known as subshells. Okay, children. Principal shell is, we are taking a first shell. We are taking first. The value of for first shell. For first shell, the value of n is equal to 1. In the case of first shell, we have only one orbital, that is 1s orbital. Suppose that we are taking second shell, we have 2 types of orbital. In the case of second shell, we have 2 types of orbital. One is a 2s orbital, next one is a 2p type of orbitals. Okay, that is the meaning of that sentence. Angular momentum of an electron also I have given. The values of angular momentum of electron which is present in an orbital, that is equal to square root of L into L plus 1 into H by 2 phi. Here L is equal to, where L is equal to orbital angular momentum. Okay, H is equal to Planck's constant. Already we know pi. It is a mathematical factor, mathematical one. So pi is equal to 22 by 7 or 3.14. Okay, next some more points are there regarding azimuthal quantum number. Azimuthal quantum number explains the shapes of the orbital. Azimuthal quantum number explains shapes of the orbital. If L is equal to 0, then it is a S orbital. Very, very important, children. If L is equal to 0, it indicates which orbital? S orbital. If L is equal to 1, it indicates P orbital. If L is equal to 3, it indicates L is equal to 3, F orbital. L is equal to 2, D orbital. L is equal to 1, P orbital. S, P, D, F. So we are starting from 0. L is equal to 0 means S orbital. L is equal to 1 means P orbital. L is equal to 2 means D orbital. L is equal to 3 means F orbital. Okay. Suppose we want to know the S orbital shape. The shape of the S orbital is spherical. The shape of the P orbital is dumbbell. The shape of the D orbital is double dumbbell. The shape of the F orbital is complex or fourfold dumbbell. Children, you have to remember always all the letters we have to represent it as a small letters only. Don't write capital letters S, P, D, F. Always we have to write as a small letters only. The significance, if you want to know the significance of azimuthal quantum number, it explains the shapes of the orbital. It explains shapes of the orbital. It is simply about the azimuthal quantum number. Next, children, you go for magnetic quantum number. Magnetic quantum number we can represent it by magnetic quantum number we can represent it by letter ML or S. ML or ML. ML. Magnetic quantum number we can represent it as ML. MOL. It was proposed by Lande. Who proposed magnetic quantum number? Lande. To explain the Zeeman effect and the Stark effect, Lande proposed magnetic quantum number. Okay. Already we know, children, what is the Zeeman effect and what is Stark effect. Zeeman effect means the splitting, the finer splitting or the splitting of electrons in the presence of a magnetic field is known as a Zeeman effect. In the last session, I have given the definition of a Zeeman effect. What is Stark effect? The splitting of, the finer splitting of spectral lines in the presence of electric field is known as a Stark effect. These two effects are explained by magnetic quantum number. The values of ML, the values of magnetic quantum number is equal to minus L to plus L, including 0. If L is equal to 0, then ML is equal to also 0. That means we have only one S orbital. If L is equal to 1, already we know L is equal to 1 means it indicates a P orbital. Then ML is equal to minus 1, 0, plus 1. Here how many P orbitals are there? 3 P orbitals are there. P orbitals are 3 types. S orbital is only one type. If L is equal to 2, it indicates D orbital or D subshell. Then ML is equal to minus 2, minus 1, 0, plus 1, plus 2. That means L is equal to 2, D orbital. It has how many values? 5 ML values. Okay. L is equal to 1 means P orbital. It has how many values? 3 values. Minus 1, 0, plus 1. L is equal to, if you are taking L is equal to 0, it has only one value, that is a 0. Okay, it is simply about a magnetic quantum number. And some more points already continuation. If L is equal to 3 is there, that indicates 5 values. L is equal to 3, that indicates F subshell. F subshell has 5 values, minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. Why we are taking this one? Because of already we know one thing. ML is equal to minus L to ML has values range from minus L to plus L, including 0. That is why we are taking these values. Okay, ML gives the information about the number of degenerate orbitals present in a subshell. What is the importance of magnetic quantum number? It explains a number of degenerate orbitals present in a orbit. If you are taking one particular orbit, in this how many degenerate orbitals are there? That is explained by magnetic quantum number. What do you mean by degenerate orbital? What do you mean by degenerate orbital? Simply, children, the orbitals which are having same energy. the orbitals which are having same energy, that orbitals are known as degenerator orbitals. In the case of p orbitals, in the case of p orbital, we have three types of degenerate orbitals: px orbital, py orbital, pz orbitals. In the case of d orbitals, we have 5 orientations. That means we have 5 orbitals. In the case of f orbital, we have, in the case of f orbital, we have 7 orbitals. We have 7 f orbitals, 7 degenerator orbitals. If you want to find the total number of ml values, if you want to find the total number of ml values, that equation is equal to 2l plus 1. Suppose that we are taking l is equal to 0, then ml values are 2 into 0 plus 1 is equal to 1. Okay, total number of ml values for l is equal to 1, then ml is equal to 3. Okay, l is equal to 1 means what, children? L is equal to 1 means p orbital. That means in the case of p orbital, we have 2 into 1 plus 1 is equal to 3. If L is equal to 2 we are taking, then ML values are 5. If we are taking L is equal to 3, L is equal to 3 means 2 into 3 plus 1 is equal to 7 ML values we have. Okay, it explains simply orientation of orbitals along the axis. Next, children, we are taking a one by one orientation. If a p orbital oriented along a x-axis, if p orbital oriented along a x-axis, it is known as a px orbital. If p orbital oriented along y-axis, that is known as a p orbital. That means how the p orbitals oriented along the axis. Based on that only we are giving the name. If p orbital oriented along x-axis, that is a px orbital. If p orbital oriented along y-axis, that is known as py. If p orbital oriented along z-axis, that is known as a pz orbital. Similarly, d orbitals also dxy, dxz, dyz, dx square, y square, dz square. How many orientations are here? Totally 5 orientations. Okay. What is the significance of magnetic quantum number? Magnetic quantum number explains the orientation of atomic orbitals. That means how the px orbital, py, pz, how the dxy, dxz, dyz, dx square, y square, dz square orbitals are formed. That is explained by magnetic quantum number. Right, children? For comparison method, easily we can discuss about the quantum numbers. Okay, till now we discussed principal quantum number, absolute quantum number, magnetic quantum number. How the who proposed principal quantum number? Niels Bohr. Absolute quantum number? Sommerfeld. Okay, magnetic quantum number was proposed by Landé. Okay, see children here, who proposed this one? Magnetic quantum number, Landé. Principal quantum number we get to small n. Absolute quantum number small l. Magnetic quantum number ml. Okay. Here in the case of principal quantum number, n indicates n. The values of n is equal to 1, 2, 3, 4 are kl mn. If the values of n increases, then energy of the orbits also increases. Right. You go for magnetic absolute quantum number. Okay. L has values from 0 to n minus 1. L has values from 0 to n minus 1. If n is equal to 1, then L is equal to 0. If n is equal to 2, then L is equal to 0 comma 1. Okay, children. Right. Next, what is the important principal quantum number? The importance of principal quantum number, it explains the energies of the orbital and size of the orbital. Next, next about absolute quantum number, it explains the shapes of the orbital. Next, what is the importance of magnetic quantum number? It explains orientation of atomic orbitals along their axis. Okay, it is the importance of magnetic quantum number. Magnetic quantum number values ml is equal to minus L2 plus L including 0. Okay, yes or no? The total number of ml values are is equal to 2L plus 1. So these are simply about quantum numbers. Next, you go for a spin quantum number. You go for quantum number. Spin quantum number we can represent it as a ms. Spin quantum number we can represent it as a ms, otherwise small s only. Okay, It was proposed by spin quantum number was proposed by George Uhlenbeck. Spin quantum number was proposed by George Uhlenbeck and Goldschmidt. It is denoted by MSRS. The three quantum numbers NLML. The three quantum numbers NLML are not enough to explain the line spectra observed in multi-electron system. Okay, that means principal quantum number, azimuthal quantum number, magnetic quantum number. These cannot explain properly about line spectra observed in multi-electron system. To explain line spectra in multi-electron system, spin quantum number was proposed. Why spin quantum number was proposed? To explain the various spectral lines in the case of multi-electron system only. Spin quantum number was proposed. Okay, spin quantum is the spin of the electron. The spin of the electron. If you are taking suppose one particular orbital, if you are taking one particular orbital, the spin of the electron in a particular orbital, we are taking suppose first electron spin, that is equal to plus of. We are taking one orbital. Okay, suppose that 1s2 I am taking helium electronic configuration, 1s2 I am taking. In the case of helium electronic configuration, what happens, children? Two electrons are filled in a 1s orbital. Okay, we are taking spin of the first electron, that is equal to the plus of or clockwise rotation. If you are taking second electron, the spin in the same orbital is equal to minus 1 by 2 or anti-clockwise rotation. That means in a orbital, if you are taking the spin, one electron has a plus of spin or clockwise rotation. In a second, the second electron has minus of or anti-clockwise rotation in the same orbital. Okay, this is simply about to spin quantum number. So what is the importance or significance of spin quantum number? Spin quantum number gives information about the direction of spin of electron in a orbital. Okay, it is the importance of spin quantum number. Children, for better understanding, one sentence I am telling how to easily remember electron, orbital and orbit. Okay, regularly in our school, where we are sitting, in our school we are sitting in a classroom. You just assume that the walls of our class like as a sphere. The walls of our class like as a sphere. Okay, now you assume that the benches, what I'm telling student, I am taking our classroom. Okay, in our classroom you are sitting, in your classroom you are sitting. Now you treat you are a electron. The children or students are in a classroom, just assume as a electron. The benches are equal to the orbital. Okay, the walls of the classroom, we have to take a orbit. The walls of the classroom we have to take as a orbit. Okay, children, understanding? If you are assuming that our classroom like as a atom, okay, now we can take as the walls of a classroom we can take as a orbit or shells. Okay, the benches are equal to the orbital. The benches are equal to the orbital. You are the electrons. That means the boundaries are we are taking as a orbit or shells. The benches, that means where the students are sitting, where the electrons are present, that place we are taking as a orbital. Similarly, where the students are sitting, that places we are taking as a benches. Students, I am compared with the electron, because all the properties of classroom depends on only on students only. Right, children? In this manner easily we can remember. You are the electrons, your benches are the orbital. Okay, the walls of the classroom is a orbit or shell. Okay, don't confuse the words orbit, orbital and electron. In this manner easily we can remember. Next, you go for the next topic, shapes of atomic orbital. Suppose that we are taking s orbital shape. What is the shape of s orbital? it is a 1s orbital. 1s orbital, 2s orbital I am taking. Whatever it may be, if you are taking any s orbital, the shape of the s orbital is spherical like this. Okay, in between, in middle of this one, nucleus is present. Okay, next you go for p orbital. Okay, what is the shape of the p orbital? I am taking here three types of the orbitals: px orbital, py orbital, pz orbital. Okay, px orbital, that means the dumbbells, the two dumbbells are present on x-axis. In the case of y orbital, in the case of py orbital, okay, the two dumbbells are present on y-axis. Okay, in the case of pz orbital, the two dumbbells are present on z-axis. Okay, what is the shape of the p orbital? Dumbbell. Okay, shape. Okay, children, double dumbbell shape. Okay, it is simply dumbbell shape. Dumbbell, D-U-M-B-B-E-M-L, dumbbell. Okay, dumbbell shape it is. If dumbbell is present on x-axis, then it is px. If dumbbell is present on y-axis, it is py. If dumbbell is present on z-axis, it is pz orbital. Next, why we are taking three only, children? According to magnetic quantum number, p orbitals have three orientations. Okay, now -1, 0, +1. That is why p orbitals are classified into only three types, right? Next, d orbital. Total d orbitals, how many, children? How can you find out d orbital? Total number of d orbital. For total number of d orbital, what is the L value? For d orbital, L value is 2. L is equal to 2. 2 into 2 plus 1. That means 12 plus 1. 2 into 2 plus 1. That means 5. Total number of d orbitals are 5 d orbitals. Okay, it is 1. It is for totally 5. D orbitals are classified into 5 types. One is a dxy, next dxy, dxz, dyz, dx square y square, dz square orbitals. What are the d orbitals, children? dxy, dxz, dyz, dx square y square, dz square. These are the d orbitals. In the case of dxy orbitals, the loops of the dumbbells are present between xy orbitals. Between the xy. Okay, dxy means the loops, the dumbbells are present between the x-axis and y-axis. Okay, next, in the case of dxy, dxz, it is x-axis, it is z-axis, xz. Okay, these loops are present between the xz axis. Next, in the case of yz orbitals, what happens, children? yz. Okay, these loops are present between the yz axis. dx square y square. dx square y square means in this case the loops are present on the axis. Here between the axis. In first three, between the axis. A fourth one on the axis. dx square y square means one loop, one dumbbell present on x-axis, one dumbbell present on y-axis. It is x-axis, it is y-axis. On the axis. In the case of dx square y square orbital. Next, dz square orbital. dz square also same. Okay, this dumbbell is present on z-axis, and moreover here some see, children, here some sphere is there. We are seeing like this. It is a dz square orbital. Totally d orbitals are 5 types: dxy, dxz, dyz, dx square y square, dz square orbitals. Next, you go for, see, children, here you go for orbital and nodes. Orbital and nodes. Already we know, children, very clearly what is orbital. What do you mean by orbital? Where the probability of finding an electron is maximum. The space of the region around the nucleus. The space of the region around the nucleus where the probability of finding an electron is called orbital. That means already easy example I said, children. Okay, our sitting benches we can treat as a orbital. That means the space of the region around the nucleus where the probability of finding an electron is maximum is called orbital. Okay, next, suppose that in that particular place we cannot find any electron. That means the the place at which the plane at which probability of finding an electron is 0. The plane at which probability of finding an electron is 0, that is called as nodal plane. That means in the case of nodal plane, we cannot find any electron. There is no electron at a nodal plane. Okay, electron present at only orbitals. Okay, right. Next we go for nodes. Okay, for this for you for competitive exams I have given some formulas. What are the nodes, how to find the nodes. Okay, nodes are nodal planes, both are the same meaning. Nodes are nodal planes, both are same. Okay, to find the number of radial nodes or spherical nodes for an atomic orbital, that is equal to n minus l minus 1. How to find out number of radial nodes, children? Easily we can find out. The number of radial nodes are spherical nodes. Number of radial nodes are spherical nodes for an atomic orbital, that is equal to n minus l minus 1. Here what do you mean by l? N means principal quantum number. N means principal quantum number. L means azimuthal quantum number. Okay, right. Next, number of angular nodes or nodal planes for an atomic orbital equal to L. Radial nodes are equal to or spherical nodes are equal to n minus l minus 1. But angular nodes or nodal planes equal to L. Total number of nodes in a shell. Total number of nodes means how to find out? Total number of nodes means total number of radial nodes and total number of angular nodes. Then we will get total number of nodes, that is equal to n minus 1. How to get n minus 1? Just you add this one, n minus l minus 1 plus l. Okay, minus l plus l will get cancel. Lastly we will get only n minus 1. Okay, this is a formula for a total number of nodes in a shell, that is n minus 1. Okay, already here given meaning of n and l also. Next, children, energies of orbitals. Energies of orbitals. So already we know, children, so many types of orbitals are there: s orbital, p orbital, t orbital, f orbital. In that s orbital, where the s orbital is present, based on that only s orbitals are many types. Suppose s orbital present in a first shell, that is a 1s orbital. If s orbital present in a second shell, that is a 2s orbital. If s orbital present in a third shell, that is a 3s orbital. Similarly, p orbitals also there: 2p orbital, 3p orbital, 4p orbital, 5p orbitals. Okay, d orbitals are 3d orbitals, 4d orbitals, 5d orbitals. F orbitals, 4f orbitals, 5f orbitals, like this. In this manner, we can find so many types of the atomic orbitals. We can find so many types of atomic orbital. Okay, so if you want to fill up the electrons, in a particular orbital, we have to know its energies. How to calculate energies of orbital? That means the energies of orbitals are calculated by n plus l rule. Which rule? N plus l rule. Okay, n means here already we know, it is very familiar to us. The principal quantum number. L is a azimuthal quantum number. So rule 1: an orbital with a higher value of n plus l has a higher energy. The orbital which has a higher value of n plus l, that has a higher energy. Suppose, children, we are taking a 2 orbital. Okay, already mentioned here 2s and 2p, 2s orbital and 2p orbital. In the case of 2s orbital, so suppose for this you calculate n plus l value, 2 plus 0. 2 plus 0 means 2. In the case of 2p orbital, 2 plus 1 means 3. 2 plus 1 means 3. It is a 2. It is a 3. Okay, children, 2 and 3. Which one has more value? 2p has a more value. That is why it has a more energy compared to the 2s orbital. Next, rule 2. Suppose that in the case of some atomic orbitals, what happen? Some of the atomic orbitals have same value of n plus L. Suppose we are taking 3s and 2p. For 3s, what is the n plus L value? N means here 3, s means 0. 3 plus 0, 3. Here 2 plus 1. For p orbital, L value is 1. That is why 2 plus 1 is equal to 3. It is 3, it is 3. The value of 3s is 3. The value of 2p is also 3. Both have same n plus L values. At this case, if the orbitals are having same n plus L values, we have to take the orbital which has more n value, the orbital which has more n value, that has a more energy. It is simply n plus L rule. By using the n plus L rule, we can calculate. By using the n plus L rule, we can calculate energies of orbitals. Okay, children. Right. Next. Based on that n plus L value, I am giving so many orbitals energy. 1s. In the case of 1s, 1, n is equal to 1, L is equal to 0, then L plus L is equal to 1. Similarly, I have given 1s, 2s, 2p, 3s, 3p, 4s, 4d. Just you observe this table, you can easily understand what is the energy filling order. Energy filling order also we can understand by Euler diagrams. Okay, Euler diagram also we can easily understand. See children, here first we have to fill electron in 1s, after that 2s, after that 2p, after that 3s, after that 3p, 4s, okay, 3d, 4p, 4s, okay, next 6d, 4d, 5p, 6, after that 4f, 5d, 6p, 7s. It is known as Euler diagram. It gives the order of filling of orbitals, how the electrons are filled, which order we have to follow, that is by Euler's diagram. Okay, next we have to discuss important principles, how the electrons we have to fill in a. So mainly we have to discuss three principles. One is Pauli exclusion principle, next is the above principle, after that rule of maximum. What is Pauli's exclusion principle? Very simple it is. No two electrons in an atom. No two electrons in an atom can have the same set of 4 quantum numbers. No two electrons have in an atom same set of 4 quantum numbers. That means no two electrons, they don't have 4 similar quantum numbers. That is the meaning of that one. So many ways we can write Pauli exclusion. Only 2 electrons may exist in the same orbit, and these electrons must have opposite spins. Okay, maximum number of electrons. How to calculate maximum number of electrons? The given by one equation, 2n square. Okay, suppose we are taking a first cell, maximum number of electrons is equal to 2 into 1 square equal to 2. Similarly, in the second shell, 2 square, 2 into 2 square into 2 means 8. In this manner, we can easily understand the maximum number of electrons in a particular shell. Okay, for better understanding Pauli's exclusion, I am given one example. I have given one example, Pauli's exclusion principle. First, I am taking helium atom. What is the atomic number of helium atom, children? Helium atomic number 2. Its electronic configuration 1s2. What is the Pauli's exclusion principle? No two electrons have same set of 4 quantum numbers. Suppose in the case of helium atom, we are taking first electron. In the case of helium atom, taking first electron. This electron for its principal quantum number 1, principal quantum number 0, magnetic quantum number also 0. But here spin quantum number, what we are taking here, plus half. Okay, upward direction indicates plus half. In the case of second electron, we are taking n is equal to 1 only, L is equal to 0, ML is equal to 3. That means these three are same. Spin quantum number vary. Here plus half, here minus half. That means no two electrons in an atom have the same set of 4 quantum numbers. It is simply Pauli's exclusion principle. That means at least one quantum number must be vary with other quantum numbers. This is simply Pauli's exclusion principle. Next, one more above principle, filling up electrons in orbitals. In that above principle, what is the above principle? Very simple, children. Lowest energy orbitals fills first. Easily we can understand. Lowest energy orbitals fills first. One sentence only, remember, you can easily understand. Lowest energy orbitals fills first. It is simply above principle. In a statement manner, I have given in the ground state of the atoms, the orbitals are filled in order of their increasing energies, or electrons first occupy the lowest energy orbitals available to them and enter into higher energy orbitals only after the lower energy orbitals are completely filled. So based on that one, I have given here orbitals energy increasing order. Okay, first we have to fill 1s electron, after that to 2s, after that to 2p. Why we are following this order? Because of 1s, according to n plus l rule, 1s means its value 1. In the case of 2s, n plus l is equal to 2. In the case of 2p, n plus l is equal to 3. That means here n plus l values are increases. That is why we are following this order. According to above principle, lowest energy orbitals fills first. After that only higher energy orbital we have to fill. Okay, above principle also given. Children, boron atom I am taking. Boron atomic number 5, 1s2, 2s2, 2p, 1x. First I filled in 1s orbital. 2 electrons I filled. After that I filled 2 more electrons. Okay, fifth electron I filled in 2p orbital. Because of in the case of 1s orbital, n plus l value is 1 only. Here n plus l value 2. Here 3. So out of these 3 orbital, 1s, 2s, 2p, out of these 3 orbital, 1s orbital has a lower energy. After that 2s orbital has a lower energy. After that this one only. So in this manner we can fill electrons in orbitals according to above principle. Next you go for Hund's rule of maximum multiplicity. What is Hund's rule? Very simple, children. Pairing of electrons takes place in a degenerate orbitals after filling up one electron in each degenerate orbital. Already we know one word. What are the degenerate orbitals? Degenerate orbitals means equal energy having orbitals. Degenerate means equal energy having orbitals are called degenerate orbitals. Okay, when we are filling electrons in the case of degenerate orbitals, we have to fill one electrons first. After that only pairing is takes place. Okay, for this I have given one example, children. See, according to Hund's rule of maximum multiplicity, I am taking nitrogen atom. In the case of nitrogen atom, atomic number is 7. Its electronic configuration 1s2, 2s2, 2p1x, 2p1y, 2p1z. See, children, I have given like this. Here what happened? 1s. According to above, we fill first to 1s. After that to 2s. Here we have a doubt because of 2p by x, 2p by 2pz. These 3 are degenerate orbitals where the electron we have to fill first. There is no question of we can fill electron in any one, no problem. But if you want to pairing, we must fill firstly one electrons in each degenerate orbital. After that only pairing is takes place. In the case of nitrogen atom, we filled 2p1x, 2p1y, 2p1z. But in the case of oxygen, we filled 2p1x, 2p1y, 2p1z. After that, we filled one more electron in 2px orbital. Here pairing is takes place after filling of one electron in each degenerate orbital. It is simply Hund's rule of maximum multiplicity. Understood, children? Very easily. Pairing of electrons takes place after filling one electron in each degenerate orbital. That is simply Hund's rule of maximum multiplicity. Okay, next stability factors. It is also very easy concept, children. Easily we can understand stability factors. Simply when the orbitals are completely filled or half filled, otherwise they don't have any electrons, then the atoms are the stable. If atoms are having completely filled or half filled electronic configuration, then the atomic orbitals are relatively more stable. Suppose that we are taking a chromium and copper. See, children, here in the case of chromium, atomic number is Atomic number 24, 1s2, 2s2. Its electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d, 5. Actually, our expected electronic configuration is here 4s2. Our expected electronic configuration 4s2. But here we write here 4s1 only because of just one electron is entered into 3d orbital, then it will be half filled. It will be half filled. That is why one 4s electron enter into 3d orbital easily, then atom will get extra stability. That is why the chromium electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d, 5. Okay. Suppose we are filling 4s2, 3d4. Then what happens, children? Atom is not a stable. Chromium atom is not a stable. That is why one electron enter into 3d orbital and get extra stability. Same in the case of copper also we can observe. Our expected electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6. Okay, here 4s2, 3d9 actually. 4s2, 3d9. But here what happens, children? To get extra stability, the electron, one electron of 4s orbital enter into 3d orbital and form 3d10 electronic configuration. Similarly, the actual electronic configuration of copper is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d, 4s1 and 3d, 10. So here, children, easily we can understand. Here half filled, here completely filled. In the case of copper, orbitals are completely filled. Here half filled. So that is why these are relatively more stable. Okay, right? It is simply about the stability of half filled and completely orbitals. Okay, right. So now, children, which questions we can expect from this chapter? So I have given here, read the questions and write answers. Okay, so write the postulates of Bohr's theory of hydrogen atom, discuss the importance of this model to explain various series of line spectra in hydrogen atom, and what are the postulates of Bohr's model for a hydrogen atom. Write the limitations of Bohr's model. Easily, children, in the case of Bohr's atomic theory, postulates, next spectra, line spectra, next limitations. These three are important. We have to learn these three topics. After that, quantum numbers, 4 quantum numbers, classification and significance, all the details about quantum numbers. They are very important. The question format like this. Planck's quantum theory also somewhat important. Okay, and some more questions we can expect. That questions I have given in your session. Okay, next in this total chapter. Okay, children, in the total chapter, what we have learned, children? What we have learned in total chapter? Simply, firstly we discussed about subatomic particles. Electrons, proton, neutron are the subatomic particle. After finding the subatomic particles, simply we discussed about atomic models. What are the atomic model? So why we have to introduce atomic models and importance of atomic models discussed. Okay, so many atomic models are there. Dalton's atomic theory, Thomson atomic model, Rutherford atomic model, Bohr's theory of hydrogen atom. These are the atomic model. After that, finally we discussed quantum mechanical model of an atom. These atomic models we discussed. After that, what we discussed? We discussed about okay, orbitals. That means to distinguish orbitals completely, we discussed about quantum numbers. Quantum numbers are also 4 types: principal quantum number, residual quantum number, next magnetic quantum number, spin quantum number. We discussed the quantum numbers and their significance. After that, we discussed the stability of atoms. Okay, and how the electrons filled in a orbital. Some rules we discussed. Okay, children. Above principle, Pauli's exclusion principle, Hund's rule of maximum multiplicity, electron configuration of atoms. So that means half filled and completely filled orbitals. These topics we discussed in our 4 sessions. Children, better to see once again all the sessions, all the 4 sessions you see one by one. You can you can easily understand total atomic structure chapter. And these points also very important. I covered all the topics, all the concepts, all the important points regarding atomic structure chapter. Thank you once again to all viewers. Thank you.
Thank you, Nageshwar sir. Indeed, you have taught us 4 wonderful sessions. So in
Yes,
each and every session, you have explained very clearly about atomic structure. atomic structure and what are the different atomic models. And then, dear children, please note that Bohr's atomic theory and along with the hydrogen spectrum, you will get for 8 marks. Sometimes you will get a split of 8 marks, like one question will be asked from Max Planck's quantum theory, and the other question may be asked from Bohr's atomic theory, that is the postulates of atomic model. Okay, so please try to learn all the principles: Heisenberg's uncertainty principle, Pauli's exclusion principle, Hund's rule of maximum multiplicity, and please try to understand the difference between orbit and orbital. Okay, so what is orbit? The space around the nucleus where the electron revolves is called as an orbit. Okay, and what is orbital? So the maximum probability of finding an electron is called as orbital. So orbital is a place where we can find an electron. Means the maximum probability of finding an electron. See how many types of orbitals are there. Because all these are the basics which you have to learn to continue for the further topics. And in our next session, we are going to learn about the periodic classification of elements. See, up to now, many elements are known. See, more than 115 plus elements are known to us. How they are remembered and what are their properties, into how many groups and blocks they are divided. About all these things, we are going to learn in our second session. So please try to watch our atomic structure and chemical bonding sessions, right? So please learn and then write down the notes, children. So we are at the end of the year. See, this is today is December 15th, isn't it? And then we are having only 15 days to complete this year 2020, isn't it? So your exams are nearing by. So please keep all these things in your mind and stay home, stay safe. So thank you, Naishro sir. So thank you very much. So thank you for your clear sessions, right? So hope you will continue your sessions for us and you will try to teach some more topics. So thank you, sir. Thank you everyone for giving us this great opportunity.
Thank you very much, ma'am, for giving this good opportunity to me, and madam encouraged very well. Thank you very much. Thanks to our additional directors are also, and Manjira madam, all the dignitaries. I heartfully convey thanks to all, and viewers. Thanks to viewers also. Thank you once again. I will maybe we'll meet again. Thank you.
Thank you, sir. Thank you.
Thank you.